Good afternoon, late afternoon, 5 o'clock, here we are. How is everyone today? Hopefully all is well. All right, and hopefully this is being recorded. I have no idea. Hopefully it is. All right, thank you very much for the feedback. So here we are tonight to talk some more about elementary Montessori. So just want to say welcome to everyone. Can you hear me all? Everyone hear me okay? All right, I'm getting a thumbs
Yes.
up. Okay.
Yes.
Super. Thank you very much because it's really hard when I can't see anyone except for one person. So I got a thumbs up. Thank you, Eric. Okay. So I want you to realize that we do move from concrete things, hands-on physical activities of things moving to abstract. Because you as adults work a lot of things abstractly, but at one point it was much easier for you to do things concretely. All right. So students develop this mental facility and imagination to see a digit as the quantity it represents. This growth continues in upper elementary, and we see this evolve in the use of the materials and the curriculum itself. So, for example, many of the math materials, we're focusing on math tonight. I think I forgot to leave that out. Um, Many of the math materials, where did I just leave off? Such as the checkerboard, we use this great thing for multiplication. And in person, I'd show you all this, but it's a little tricky right now. And these things we call the test tubes for some division work. And they're designed to let the children actually move things to form the calculations, using beads and bead bars and calculations done abstractly. And by abstractly, I'm always referring to paper and pencil. Yes, sometimes people do it in their heads, but I am really referring to paper and pencil for abstractly. And there's other math materials that allow the child to see concepts, such as operations with fractions, percentages, geometry proofs, and the squaring of a binomial. Those are physical manifestations, and they make the abstract more understandable. Students don't even realize how much they're understanding until it all culminates and comes together. And it's really great to see in some 6-year students, they're saying, that's why we did this before, and that's why we did this before. And I'm like, oh, you're pulling it all together now. It's awesome to see them do this. And so through these Montessori materials, students literally grasp the meaning of the math at the same time as they're working on their understanding of these abstract concepts. And that's something that we really need to keep in mind, that they are gaining and gathering information constantly. And then they get to put it all together later on, and they're just like in awe and saying, wow, I know how to do this. This makes sense to me because of such and such and such and such. So this, I'm talking about it in regards to math, it really affects all areas of study. Grammar and sentence analysis, those materials work while you're grasping knowledge about how our language works. How do you put it together in your own writing? Everything are all these little steps to help them reach mastery across all the different verticals, the academic verticals. So the upper elementary student is developing the ability to think more abstractly in terms of time. Whereas for a younger child, they say, what's going on now? Or it's not now. It's either now or not now. The older elementary child can think beyond the here and now to other lands and cultures existing across time. Upper elementary students use this growing imagination to see how their own lives may unfold across time and space. The UE cultural curriculum of history, geography, and science includes studies of ancient civilizations, and we're going to get into more ancient civilizations here as the evening goes on. And the UE student takes these seeds of culture, these little tiny bits, and they germinate and watch them grow in their imagination and their understanding of the whole world. Because they're trying to figure out how they fit into this wonderful world that we have. All right, so they're taking these little pieces and seeing what they can do. So we need to remember that the materials themselves, they don't do the teaching. I don't do the teaching. Rather, all these materials provide a vehicle for the children to make their own discoveries while they're exploring and creating these aha moments and as they're learning for themselves. We guide them. The children are doing the learning. No one can force it on them. All we can do is encourage them to explore and make their own discoveries and see what they come up with, great inventions for our world to come. And so tonight, we're going to be talking about this great fifth story, one of the great lessons of Montessori. It's the fifth story, the story of mathematics, or numbers. Some people call it the story of numbers, the history of mathematics. They're all called all over the place. But anyway, this lesson is presenting the math and the geometry presentations that explore the history of a particular concept at the same time that its presentation is given. So we go back into ancient times to look to see how things were done before, so we can understand how things developed and how other people did their exploration, so that we can do our own exploring in our understanding of these different concepts. So this story of mathematics, this history of numbers, along with the history of writing and communication that Catherine talked about last night, these lead all into the studies of the ancient civilizations, because that's where these things begin. As far as we know, that's where they started to be developed. And so there's this person that I've learned about. His name is Michael Dorr. He's a Montessorian, and he's a great storyteller. I've listened to him give many stories, and I just get engaged and he draws me right in the way he tells stories. And I have a book, and I use many of his stories for the students. Now, some of the stories have to do with area, some have to do with grammar symbols, some have to do with the history of numbers, which we're going to do tonight, all different areas of cosmic education. And I tend to start many of our areas every single year with different impressionistic stories. And I don't do the same ones for every year, so that students who are with me multiple years, which hopefully all of them, they will hear different stories, different manifestations, and from different perspectives, because we all need to hear and learn things from different perspectives. Okay, I believe that's how we figure out our own perspective. So every story is different, and we don't do them all on the same day, that's for sure. That would be way too much for the children. And so I'm going to start off to give you a feeling of what these stories are, how do I say it? How these stories are heard by the student, by trying to get you to be in the mindset of a student. So take a deep breath and think, all right, you are 9, 10, 11, 12 years old. And you're going to just listen and let your imagination go as I read a story to you to see where it takes you. This story is called The Dawn Child. We're taking a trip. We're going back far in time, to a time so long ago that we have lost count of when it is. Back when people were living in caves, when there were no houses. One group of people lived in a cave overlooking a beautiful, beautiful valley. They could look out and they could see green grass, many trees, a watery stream, and the lovely valley beneath, frequently traversed by many different types of animals. This story is about one person, one special person that lived in that tribe, a girl whose name was Dawnchild. The girl called Dawnchild because she rose early every morning at the time of the dawn to see the animals and the warm light that illuminated the sky at that time. Dawnchild loved so much to go down into the valley close to the river. There she would see the birds and the fish. She would see amphibians and animals in the trees. And she would see large animals that had come to drink. She loved to follow the hunters and watch them when they went out to chase animals, great or small. Sometimes the hunters chased animals as small as the hare or the squirrel, and other times they were to find large animals like deer or caribou. The wise woman in the tribe frequently told her, "Dawnchild, Hunting is not for you. Hunting is for the men of the tribe. You are not to go with them." But Dawnchild wanted to go, and she loved to watch the hunters when they practiced by putting a stone into a sling and whirling around their heads again and again until they released it forcefully at a tree. In this way, they perfected their technique so that when they were out hunting, they would throw the stone to easily catch a rabbit. Dawnchild also loved to watch them when they made a spear. The hunters made the head of the spear very carefully with flint. They would take their spear and put it into a wooden spear thrower called an atlow. She watched them practice throwing. The spear would go at tremendous speed and very accurately towards a target. Over time, Dawnchild learned how to do things too. She watched and she learned how to whip the stones, and she watched and she learned how to throw the spear. She became an expert at using these things. She learned to knap flint and make sharp knives and spearheads, and eventually she became a hunter. Even though people had warned her not to do this, she was respected because she could do these things. When they went on a great hunt, they needed to consider how they would carry back the food, for one person could only carry so much. If one person went far away and found many, many caribou, it would be impossible to bring all the meat and hides back. So when they went on a long hunt, there was always a question of who should go. Should everyone go? How many people were really needed? Answering these questions was always very difficult because in these days no one knew numbers. There were no numbers and counting, and that had not even been invented. The only thing could be counted was one thing, something by itself. One day, Dawnchild went quite a ways away from the tribe's area. She went about as far as she could run in 2 whole days. She ran and she ran until she came to a high ridge that overlooked a broad plateau. And in that plateau was a beautiful set of pools. Maybe just right for animals to come and drink, she thought. She stayed there through the night until the next morning. Then she could watch at her favorite time, the dawn, to see if animals would come and drink. And they did. There were many caribou, enough to feed her tribe for the whole winter. She knew that her tribe could eat well and live if they could only kill all of those caribou. But she also knew that she could not carry them all back by herself. She was frustrated because she feared that she wouldn't be able to tell people how many hunters were needed to come back to help. As Dawnchild sat there, thinking and looking over the plateau, she happened to be holding a stone in one hand. In her other hand, she held a stick. She was idly scratching at the stick, and she was thinking, just sort of absent-mindedly, scratching away at the stick. What to do? What to do? Scratching and chipping away at the stick kind of helped her to think. You know, sometimes we need fidgets. When she looked down at the stick, suddenly a great idea came to her. She made a sort of mark on the stick, and she stared at it with her forehead furrowed in concentration. For some reason, it occurred to her that the mark was like a caribou, just like one caribou. Not a herd, but one. She made another mark on the stick. Dawnchild looked and she thought, and this mark is also like one caribou. And she scratched another mark and thought, this is also like one caribou. Dawnchild kept making markings, one and one and one and one and one, until she made one mark for every caribou that was there. One and 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 one, a mark for every caribou she saw. Many caribou, many marks on Dawnchild's stick. Dawnchild picked up her stick and began to run. She ran the long way all through the day and most of the night. She ran all the way back to her village, to her cave, to her tribe. They were hungry, but her people would not be hungry for long, for when she reached them, she also thought something, that one mark is like one hunter. One and one and one and one and one and one and one were needed to go find the caribou and bring them back to the tribe. Dawnchild's idea worked. The hunters were very successful. They had exactly the right number of people to carry exactly the right amount of meat back to her tribe, and they ate very well that year because of Dawnchild. Now, Dawnchild really wasn't counting because she could only count one, but she could count one many times, so that is what she did. Today, we call that stick that she used a tally stick, and the scratches that she made we call tally marks. By making those tally marks, Dawnchild started something wonderful, which was the beginning of counting, the first step leading to humans being able to count. People discover things when there is a need. Those early people had a need, and Dawnchild discovered it. That probably happened more than 25,000 years ago. I guess I should say that the wise woman never again told Dawnchild that she should not hunt, because Dawnchild had proven that she could do just that. Dawnchild showed that she was not only a person who loved the dawn, but she was also a great hunter and inventor. And after reading that story to the children, we let them think about it and sit on it and think about it. And we may have discussions. They always want to talk about things afterwards. And they bring up different points, and it just gets their imaginations going and saying, well, here's a story. Maybe it's true, maybe it's not true, of how counting may have begun, how some very early human figured out a way to do things when they needed to. Just like when we have problems and we need to come up with solutions, we need to come up with a way to solve our problems, just like Dawnchild did. And so this carries out through all areas of our lives, in the whole person. And we work on that. And we let the children sit with these thoughts and see where it takes them. And then on another day, we tell them another story. And it's the story of numbers. Now, you may have questions that are being provoked, and I guess I should probably hold off questions till the end so that we can continue on. So I want to continue on. So another day is passing by, and I'm going to share my screen because on this next story, we get a little bit more involved with the children with showing them some pictures. So instead of being straight impressionistic, we get into more of the actual history of the numbers and how they come on. Because at the same time, realize students are studying different ancient civilizations. They've looked back at some of these early humans. What were they doing? How did words come about? The noun is what we believe to be the first word of our language, spoken words. Okay, and so we've looked at some of that. We've looked at the coming of humans and how special humans are to the world. And so we look at Mesopotamia and Babylonia and what's going on and what happened and what did the Romans contribute. And recently we were looking at Egypt when we were studying Africa and looking at a lot of things that happened back in ancient times on that continent of Africa. And we look at each continent at different times, different years, as we're studying these different ancient civilizations. So they are exposed to what's going on back in ancient times and building upon those. And so all that comes in, and now I am going to actually share my screen. So you should see up on your screen now the story of numbers. and a bunch of different numbers. Okay, wonderful. So this would be now another day where we're going to dig deeper into this whole thing of what are our numbers, where they come from, what's this counting business, and what is math, and what do we do with all of this. So this is a completely another day now, and we're going to dig a little bit deeper. And so this story is the story of numbers, and we're going to take us throughout the time of humanity and show us many gifts that we have been given. So many different people around the world that have allowed us to have the number system that we use today in mathematics. So for this story, we start off looking and saying, well, where did this all begin? And in our timeline of life of the coming of humans, there's a picture of a person milking a goat. And we say, well, that symbolizes that humans were learning to domesticate animals, which greatly changed the animals from their wild ancestors. They were learning how to domesticate animals to benefit and fortify their lives. So the domestication of animals revolutionized humanity too, because humans no longer had to travel and be nomads going from place to place following a herd of animals in order to get food to eat. Instead, they could stay in one place, and staying in one place meant that they were better able to meet their physical needs of food, shelter, and clothing. Now, they could work on some of their other needs, and this allowed other human inventions, such as mathematics, to flourish, even though those inventions and discoveries came from very simple beginnings. So during this ancient, long ago time, about 6,000 years ago, there was a shepherd called Epeli. His name meant meadow, and he had been named that to honor his future work, which could be, or would be, as a shepherd, herding his flocks in beautiful meadows. Epeli would let his sheep out to graze in a meadow during the day, and he would bring them back into his pen at night. Epeli could not count, but it was very important to his livelihood to keep track, and his family to keep track of those sheep very closely. He could not afford to lose even one sheep, for his family depended on them. So, when he would let in his sheep out of the fold in the morning, Epeli would put a stone in a pile for each sheep that passed through the gate. Then he went off for the day and worked, and at the end of the day, when he called the sheep back in for the night, he would take a stone out of the pile for every sheep that returned. This way, if there was a stone left, he knew that there was a sheep missing, and he needed to go and search for that sheep. Even though Epeli didn't know how to count, he knew how many sheep he had by using the stones in a one-to-one match to represent sheep. Got our ratios going. That was one of the earliest forms of counting, and it was very similar to Dawnchild and her notched counting stick. So other people were learning to count in this way too. Some of them made notches on sticks or antlers. Some would use stones, and some of them would even carry along a rope into which they could tie and untie little knots as they counted. Can you imagine a shepherd tying a knot in a rope for every sheep that he let out, and then untying each knot when the sheep came back in for the day? Well, that's how people started to keep track of their things. Eventually, people invented words for numbers, and those have led to the number names we still use today. No one knows for sure where those words first came from. Humans have only ever invented numbers for the amount of things that they need to count, for things they had in their environment. And so it's taken a great time for numbers to grow as high as we can count today. First, people just needed numbers in the units, and tens, and then hundreds, and thousands, and 10,000s, and 100,000s, and millions, and today we have a Google. Okay? 10 to the 100th, we even have a Google. So numbers have grown as humans have needed them to. So now let me tell you another number story. the people of ancient Egypt were blessed with a great river, the River Nile. It flowed northward through the country. The Nile also flooded almost every year. The water went over its banks. And this made the land around the Nile very fertile for farming. The Egyptians were lucky, because meeting their basic needs of food and clothing and shelter was helped by the Nile River. Just like the Babylonians, the Egyptians, with their fundamental needs met, were able to develop more things. And both numbers and writing flourished because they had time to explore with them. In fact, ancient Egypt is considered one of the greatest civilizations of time. The Egyptian king was called the Pharaoh. So the Pharaoh was responsible for everything, and he owned everything. Of course, as owner of all things in Egypt, he wanted to keep track of all the things that he owned. He wanted very precise records kept, and the Egyptians had a special way of writing. We call their writing hieroglyphics. And it was actually the Greeks that named it that. Hiero meant sacred, and glyph meant carving, thus sacred carvings. Yes, the Egyptians actually carved their writing in stone. Imagine how precise those stone cutters had to be to keep those precise records and carve them into stone. Well, we still have evidence today of their stone-carved records, and this is one of the reasons we have been able to study and learn so much about the Egyptian numbers. Now, their first numbers were very simple. They were just strokes, like you can imagine, tally marks. 1 stroke for 1, 2 strokes for 2, 3 strokes for 3, and so on. Well, that system didn't work very well when they got going and get into higher numbers. It would take too long to count so many strokes. So the Egyptians invented special symbols to represent certain numbers, and then they would put together multiples of those symbols to make other numbers. And so a 10 looked like this. Many people that this is a symbol of a hobble, a special device that would go over the neck of their oxen so that the oxen could pull the heavy loads. Others believe that it represents a heel bone or even a twist of a rope. The symbol for 100 looked like this. It was a coiled rope. The symbol for 1,000 was a lotus flower. The symbol for 10,000 was a crooked finger. The symbol for 100,000 was a tadpole. And the symbol of 1,000,000 was a god or an astonished man with his arms raised towards the heavens. The Egyptians carved and used these symbols to keep track of the things in the Pharaoh's kingdom. Could be that the million was, I've had enough. All right. Now, the counting system that we use is based on 10. It's called the decimal system because it's named after the Latin word for 10, which is decim. Not all people use a base 10 system, and in the past, other systems were used as well. Some of the oldest numerals known were used by very ancient civilizations such as Sumeria. The Sumerian numerals existed as early as 8,000 years ago. Okay. Then later, the Babylonian number system emerged. It is very ancient, and it is possibly as early as 2000 BCE or 2100 BCE. By then, there had been their own system of counting based on the number 60, because the Babylonian system is credited being the first known positional or place-valued numeral system. The farmers at that time were trying to figure out when to plant their crops, because there was a time of year when it would always flood, and they realized that it was necessary to consider this for their planting plans. And they tried to solve this problem and formed a belief that when the brightest star rose before dawn, it always began to flood immediately after that. And so they started counting. How many days passed until the next time the brightest star rose in that exact spot in the sky before dawn? They counted 360 days. Were they right? Now, we know there are 365 and 1/4 days in a year. They were close, weren't they? And they were very, very close. Well, they took that cycle of the year and they divided it into 360 parts. And we still divide our circles into 360 parts. And we call them 360 degrees. And that's all based on the Babylonians and their cycle of the year. Can you think of other things that we still use today that are based on the number 60? Think. Look at your clock on the wall. I wonder what that's based on. We have 60 seconds in 1 minute and 60 minutes in 1 hour. So we can also, here in our time, see the Babylonians' influence on us. The city of Babylon was built upon the Euphrates River and divided into equal parts along its left and right banks. This was not too far north from where the Tigris and the Euphrates rivers met. The Babylonians were cuneiform writing. Cuneiform is a type of writing made with wedge-shaped marks that are pressed into clay tablets with a blunt reed. You may have heard of something about that or remember that from the history of writing. The people were able to dig clay from the riverbanks, and they harvested reeds that naturally grew in the wetlands along the river. When they were cut a reed in a particular way, they were able to make a triangular shaped stylus, a writing tool, that they could press into the clay. When they did this, it made a U-shaped imprint that they could make either small or large. They could also give the impressions different orientations in the clay by changing the direction that held the stylus. Maybe we should try some of this. So the Babylonians, 3 in cuneiform, look like this, wherever it is. And they pressed their stylus in 3 times. A 10 looked like this, and they would turn the stylus and press it in a 60. Of course, as its larger special symbol, because their numbers were based on 60. And I forgot to click a couple slides. There's the 3, and there's the 10, where they would press it in 3 different ways. Now, the Babylonians traded with many people in the area around the Mediterranean, and they kept track of their trades. If, for example, they sold 3 bowls, they would make their symbol for a bowl and then put 3 tally marks underneath it to keep track of that. Because they were doing this on clay tablets. They were able to bake those in the sun, and they would harden. These tablets were like the first form of receipts, where they were able to preserve a record of their transaction, of what they purchased. Some of those were very basic transactions of traders at markets, but archaeologists have also found great stores of these clays that have been kept. By studying these, we know that the Babylonians were able to do some very complex mathematics. Some tablets used fractions, algebraic formulas, and even the Pythagorean theorem. The Babylonians were actually doing some very advanced mathematics. Now, in another part of the world, the Hindu people of India developed numbers that led to our numerals today. Their numbers, 1, 2, 3, look like this. They had tally marks. They did them horizontally. Their numeral for 10, though, was quite different. You can see the 10 down below. The Hindu people of India also left us another great gift, a huge, huge gift. We are so lucky that the Indians left behind this wonderful, incredible, glorious gift. Can you imagine what this gift was? Do you know? Do you want to try to guess? It was nothing, nada, zilch, nula, 0. That's right, 0. After all, somebody had to invent the idea of 0, and it was the Indians. Around 600 AD, in the Indian language of Sanskrit, 0 was shunya, which meant void or empty. Now the 0 carried incredible power, because then, in their language, they were able to create large numbers by simply adding a 0. That was very first 0 was just a small dot. And this powerful, wonderful, almost unbelievable idea that the Indians invented worked so incredibly well that the Arabs, who were trading with the Indians, picked up on it. Yes, eventually, although it took hundreds of years, The Arabs caught on, and they started using the zero too. They saw how quickly the Indians were able to calculate things when they were doing trades because of the great and powerful zero. Some people still argued against having a zero. They said, zero is not a real number. How can you have a number that means nothing? If zero means nothing, then it's not a number. The whole point of numbers is to count things. And if you have nothing, then you're not counting. If zero was a real number, you should be able to divide by it. All of those were the arguments against zero. But the Arabs had their own arguments. They had a powerful one, which was that zero actually worked for calculations, and you no longer had to use an abacus to calculate things if you had zero. The Arabs became the real inheritors of the Indian system of numerals, including the zero. The numerals they developed looked a lot like our numbers today. In Europe, though, the Romans had developed their own system of keeping track of numbers. You may be familiar with these. They are called Roman numerals. They were based on 7 signs. The I was 1, the V was 5, the X 10, the L 50, the C 100, because the C stood for centi, which meant 100. You'll see that the root used in many Latin words, like a centurion, the leader of 100 army troops. A D was 500, and M, 1,000. The Romans made a rule that the order in which you arranged the letters indicated whether you were to add or subtract. If the smaller number came second, you were to add it. So, xi equaled 11. If the smaller number came first, you were to subtract. So, ix equals 9. Where have you seen Roman numerals? Have you ever seen them? Have you seen them on anything? Think about that a moment. Sometimes we find them in our books as the chapters are counted in Roman numerals, or on clocks. Often, on important buildings, you will see that the date it was built is recorded in Roman numerals for some reason, etched in stone. Today, even our Super Bowl always has the year recorded out in Roman numerals. Why do you think that we use Roman numerals for these things? It's a system that works very well for counting, but it isn't very good for calculations. Imagine trying to do a multiplication problem that looked like this. It gets a little tricky. So the Romans, instead of doing their calculation numerals, had a special device called an abacus. You can think of an abacus as being a little like our bead frames, where beads represent numbers and you can manipulate them with a stylus to calculate. When they finished their calculations, they wrote out their answers in Roman numerals. Meanwhile, while this was all going on in Europe, the Arabs were trading with people in Europe. Of course, they used their numerals to keep track of buying and selling. The idea of the Arabic numerals, Indo-Arabic numerals, had simply traveled with the Arabs and spread over to Europe. They brought that system to Europe about 1000 AD. Can you believe this? The Europeans didn't want it. No, they did not want these numerals. They did not want an Arab idea to spread. However, those numerals were such a good idea that they spread anyway, especially with merchants, traders, and sellers. They liked the Arabic numerals because they could easily use them for the math. Although it took centuries, the transition from Roman numerals to Arabic numerals was finally accepted. Our numerals and our way of calculating today were based on Arabic numerals. In fact, that is why when we add up our columns and numbers, we go from right to left, just like the Arabs read. And here's an example of a book, which is a page in a book of Algebra of Muhammad bin Musa, which you read actually from right to left, if you can read Arabic. The Arabs had many great gifts to give to us. In approximately 830 CE, a Muslim scholar called Muhammad ibn Musa al-Khwarizmi forgive me if I pronounce it wrong, wrote a book about calculation. In his book, he discusses an operation that he called algebra, which meant completion. What does algebra sound like? It sounds a lot like algebra, doesn't it? Well, that's because algebra is where the word algebra comes from. And I have another important discovery to tell you about. In the 17th century, there was a German mathematician named Gottfried Wilhelm von Leibniz who made a system where it's possible to count using only 2 digits. Now, at that time, everyone thought he was crazy. They laughed because his system looked so strange compared to the numbers that everyone was used to it at that time. The idea that Leibniz had was that by only having 2 digits, you could have a switch that was either on or off. So, 1 looked like a 1, a 2 was a 1 and a 0, a 3 was a 1 and a 1, and a 4 was a 1, 0, 0, a 5 a 1, 0, 1, a 6, 1, 1, 0, and so on and so on. People thought this was preposterous. They laughed at him and told him that this was the craziest thing they had ever seen, that no one would ever use this system of counting. Aha! Well, guess what? The system he invented way back then is now called the binary number system. It's true. He invented binary numbers. Leibniz's discovery wasn't used for 300 years, but now it powers every computer in the world. That's right. All the computers use binary systems for their calculations. People may be laughing at this new mathematicians, but who knows? Maybe any new mathematicians coming along and their discoveries will have a great future too. We must have gratitude for all of these past explorers that came before us and gave us these gifts of mathematics that we have and use today. Thank you to the early humans for their notch counting sticks. Thank you to the shepherds like Apolly who counted with the rocks and the rope. Thank you to the Babylonians for counting our year, for dividing our circle, and for keeping time. Thank you to the Egyptians and their stonecutters for their precise hieroglyphics. Thank you to the Romans for the Roman numerals we still use today. Thank you to the Indians who came up with the great, stupendous idea of 0 and gave us the power to calculate. Thank you to the Arabs who believed in that great 0 and who developed the numbers as we use today and spread them around the world. Thank you to all the mathematicians of the world who've made mathematical discoveries. Thank you to all of those who came before us. Just think about this. Perhaps you, in this very class, will be the future mathematician or mathematics explorer who will also make a great discovery to help all people, just like some of these others. And that's the story of numbers. All right, so we have this wonderful story of numbers. And again, we let students ponder over it a little bit. We don't just immediately go jumping into anything. Sometimes we say, just reflect on it. Write some of your thoughts down right now. It's something that you might want to go back and look at sometime. Okay? We have these different stories. It gets us thinking. It gets them thinking about how does this fit into the civilizations that they have been studying? How does it all work out together? All right. So we take these. Oh, here I can stop sharing my screen. Stop share wherever you are. You're hiding from me. So we can take these discoveries and these stories. We're thinking about where all these numbers came from, all these different pieces, the power of these numbers. And we carry them out in a lot of the things that we're studying around the room. It comes into our geometry studies, where we're trying to find the area of a triangle. And I can show you something on that as we contemplate. Let me Oh, the doc ID camera's not connected. As we contemplate going around, I'll just plug this baby in. Change the microphone up. Okay, so as we look up, I'm losing my video here. There we go. All right, so here we have the history of money. And we look at the history of money. Here's how numbers came to be. And this follows up with some card works and things so the children can go and explore and refresh their minds on different areas. And they can read more information and more, and then which often kicks off them into researching even more about different things that affect them or they find interesting. We can get into the history of measurement, all things that are related. Something else we can look at is we can look at our geometry. And this material actually stems from another story about our friend Marigold and her brothers and how they try to figure out farming. And we're not going to go through that whole story right now, but it's a story that tells you about how they figured out square units is necessary for figuring out area accurately so that they could measure their plot that they were farming. But we look at things and we carry it through in the curriculum. And we say, how do we figure out the area of a triangle? And luckily we have different pieces in our material sets. And we can say, oh, isn't that a nice looking triangle? Well, you know what? We've already figured out, if we count the squares, we can figure out the area of this rectangle. And we can count and we can see that it is 10 squares across, all the way across this space. And we can go up the height and we can see that it's another 10 squares up the height. And we could go and we could count every row, or we could count every column. And we're looking at the square units, and students go through an exploration to realize that they need squares. And they measure the area of things all over the classroom. They're trying to figure out these different, what is the area of the tabletop? What's the seat of the chair? What's the binder? What's the whiteboard? And they're taking all these red squares and going around and measuring them in square units to reinforce that it needs to be a square unit. And we can do that story another time. Or ask your students after they have it. They could probably tell you the story. They love that one. But then we get into deriving the calculations. And we don't just tell children the formula for finding the area of a triangle. They have these pieces and they could say, oh, look, I could superimpose this triangle on top of the other triangle. Oh, that looks nice. It fits perfectly. And they've already done a study of equivalents, so they know all about equivalent shapes. And they've looked at the rectangle and say, oh, well, we've got the area of a rectangle. But I just cut my rectangle and I was able to form two equivalent triangles. So because I could form two equivalent triangles, they very quickly figure out that the area of this triangle is half of the area of this rectangle. And so then we start calling things with names where we have a base and a height, and they figure out that, oh, the area of the rectangle is 2 times the area of the triangle. You could take it that way, because now I have 2 triangles. So it's 2 times. That means that I could also switch things around, and we can get into some algebra, switching formulas around and looking at what are the missing variables, that our triangle takes the base and the height, which is what we use to calculate that of the rectangle, and divide it by 2. Because the area of this triangle is half of the area of its rectangle. And so we get half the base times the height equals the area of the triangle. And we do these different calculations just as people in ancient times did these calculations on geometric figures. And one of the beauties of the whole thing is when they discover the formulas by moving the pieces around, I say, okay, you figured out how to do the rectangle. Go ahead, go, move the materials around, work with your numbers, count the squares, do different things, and see if you can figure out how to find the area of the triangle. So they find the area of the acute triangle, and then we look at the other 6 different types of triangles and try to find the area. And then they come to the conclusion that, hey, every single triangle, I can take the half of the base times the height. And they come up with all these things. But what it is they are discovering it. That is the key to it all. When they discover it and they figure it out, that's when they tend to remember it. And that's one of the beauties of the Montessori education. They get their hands on it, they manipulate, they explore, they're getting a clear understanding. Like I said at the beginning, when they're moving those materials around with their hands, they are grasping the understanding to do it abstractly. And where's my whiteboard? And once they start doing it abstractly, then, and I did lose my whiteboard, then they start looking and we can move on to other areas and say, all right, I know the base, I know the area, but I don't know the height of my triangle. So then we have to, the formula gets moved around. You know, you've got the formula all figured out now. Now you get to manipulate it. And we get into algebra. They don't realize they're getting into algebra, but they're getting into algebra. Okay, just finding the unknown, using, you know, B for the base and H for the height. They're using variable names. And it just starts growing in them naturally versus, oh no, here's this whole new thing I've got to go learn and do it. They just grow with it. And it's a beautiful thing. Just they don't realize how much they know after doing these things. So I wanted to show the example with the area. There's another great thing. And I just have the plastic inserts here. I'm going to put you back on the DACA-D camera. Here I have one hole. And this is, one hole can be a beautiful thing. One hole can be broken up into 2 halves. One hole is equivalent to 2 halves. And all through lower elementary, they go through and they create equivalent. They start with metal insets, and then they move to this set of fraction pieces. And we could also have 3/3. And they come up with all these equivalent fractions as they are understanding that these all are the same thing. You can have one whole in many different forms. And then over the years, we start using these different forms for doing different operations. First, you learn how to add fractions. If I've got 1/3 fraction and I want to add 2/3 fraction to it, aha, I end up with one whole, 3/3. They're doing it with like denominators first. Then we get into, well, what happens if I want to add, I'm looking for an easy one. If I want to add 1/2 fraction plus 1/3 fraction. Well, how can we do that? Well, they learn, again, they've been working with their equivalent fractions. So they're saying, well, I don't know, let me see what I can do here. I can take 1/3 and I can replace it with 2/6. I can replace my 1/2 with 3/6. If I change my 1/2 to 3/6 and my 1/3 to 2/6, I can add all my 6 together because then they're in the same family and I'm very comfortable with doing that. And so I can see now that I have 5/6. Again, through the materials, they're getting an understanding of what it is by looking at it, feeling it, seeing it. So that then it's not just doing magic on paper and following a recipe. I know from some of my own experiences with children that have not had the benefit of Montessori education, that pushing the numbers and following the recipe, often they miss the whole understanding of what is going on. And when they get into higher mathematics, they get very troubled because they're like, it just doesn't make sense. And it doesn't make sense because they never understood the basics. Now, granted, I have had people say that here in this classroom, that it just doesn't make sense. And I say, go get the materials. And then they come back to me a little bit later and say, I got it. It makes sense now. This is why it happens. Da, 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 da. And they spill out everything. They just needed a little refresher with their hands on the material to understand what was going on and why. So it's a wonderful thing. I mean, I could go on like all day, all night, teaching you more and more of these different lessons because they are so fascinating. There is a great one with division of fractions, and we use these symbols, and you do distributive division. And I am set up to do that, but I am also cognizant of the time. And if you have particular questions, I would really love to try to answer your questions that you have. I mean, this is targeted to look at all of the curriculum. I'm definitely focused on mathematics with the story of numbers and how numbers came to be, and gave some examples. But if it triggered any questions on any of the areas, I'd be happy.
Rita, there are 2 questions in the chat. Would you like me to read them, or can you pull them up?
I just pulled it up. Is the highest level of math taught algebra? Depends. Through our geometry approaches, the children do geometric proofs. When I mentioned earlier that they are doing the equivalence of shapes and figuring out what that is and figuring out if things are equivalent, they're doing a proof. So depending on what you say is higher, because often in high school, you take algebra 1, then you take geometry, and then you take algebra 2. It's kind of a common sequence of events that takes place. So it's across what's higher, geometry or algebra. Depends what level of algebra as well, because you can keep going in algebra. So I wouldn't say ever that there's a maximum level that is ever taught here through the 6-year student. I will try to reach the student wherever they are. I do have a degree in mathematics, and I'm pretty comfortable of carrying students farther if they are ready for it. But I do want to make sure that they are well-rounded and have a good foundation in all areas. No one has pushed my limits yet. And if they do, I have people I can go talk to try to get some more information to help these students along. Hopefully that answers your question. As far as trigonometry goes, that gets more into the angles, and that could come into play very easily. Would it be an outright course in trigonometry? No, I don't think that any of them would be truly ready for a whole course in it, but for some of the basic concepts, they will have those. Just from looking at angles and our study of angles as we continue on. They have had some angles already. They do that, a lot of it in lower elementary. We carry it on and go further when they get proving of things, both area and volume, then they are using some trigonometry, whether they realize it or not. So sometimes that does come into play. I've never had anyone get into any abstract algebra or topology at this level. We might talk about different bases other than base 10 number systems. That is a common thing that we get into as well. I mean, yes, we've got base 10 and binary, but we can get into base 60 on many fronts as well. And they could even start translating things to a base 8, base 7, you name it. Students are capable of doing that. All right. Any other questions? I like questions. Questions help give me an angle to talk on.
There's a question saying, do the upper and lower elementaries hear the stories at the same time? Unfortunately, because of COVID, the classrooms are separated, so they do hear the stories at different times.
Yes, they do hear the stories at different times. I believe, for example, I believe lower elementary has already had the story of writing. I'm planning on doing it in about a week. Different things going on. We dive into different things. Depending on the students and where their interests are lying. Often we hear common stories between lower and upper elementary, In upper elementary, I like to take them a little bit deeper and tie them into some other studies that they are doing. They do, upper elementary does deeper studies on the ancient civilizations. So it brings more of these stories to life. And I try to touch upon that to make the students aware and for them to, I encourage them to make more of those connections. And it often raises more questions, and then we have to research and dig a little bit more to find answers. So sometimes our timelines are different.
Hey, Rita, do you mind if I comment on the stories?
No, go right ahead.
So in my training, I've heard that story many times too. But I get something out of it every time I hear it. And even tonight, I got something new out of it, listening to you tell it again. I was thinking about how the different contributions to mathematics was chastised and kind of made fun of at first. I was thinking, wow, that could be that sends an encouraging message to kids, about pushing through skepticism when you have an original idea.
Exactly. Exactly. For them to say, Dawnchild, you don't belong to be out there being a hunter. Well, she certainly is capable. She can go right along and do those things. And, if you want something, you've got to strive for it, but you can do anything. There are no limits for any of these humans. Yeah, and it is a wonderful message that is reiterated in many ways. So it's a good thing. Thank you very much. And the stories differ. I don't, like I said earlier, I shared a version of these stories with you tonight. I do not do these same versions every single year. I purposely turn them up and change different stories that I have read, and sometimes I merge some together because I want students to hear different perspectives. And they might connect to one version more than another. That's all possible as well. All right. Any other questions stirring in your minds? We're looking good then. All righty. Does anyone want me to go through a division of fractions lesson? Thumbs up, thumbs down, thumbs sideways. I can do that if you would like. Oh, I'm seeing a thumbs up. All right, I can do that. I'm going to switch you back to the Doc ID camera so you can see the materials as we're going through here. So here we can do, I should grab my whiteboard wherever it went. I'm looking for my whiteboard. We will do a fraction division problem. And in the fraction division problem, we can choose to do in a very physical, hand grasping way. That's about right. So if we say, I don't know, we can take a whole number. We can take 1. Actually, take 2. Let's do something a little more. 2 divided by 2/3. Oh, my marker isn't very good here. 2 divided by 2/3. Make that a little bit darker for you. And people are like, 2 divided by 2/3. And we have students that are doing many as they're looking for patterns and things as they're doing these problems, because we purposely do not want to share any tips and tricks with them. We want them to discover some things on their own. So we have these rather large thimbles. And these thimbles are broken up into some different pieces. This one is broken up into thirds. So it stands for thirds. So we say, all right, we can take our 2 wholes and we want to divide it by 2/3. So here we have, and I guess I need to get this up a little bit higher. We have our thimbles and we have 2 of them, because that's 2/3. Well, then we have another one that we'll stick off in Timbuktu and say, all right, we don't need that guy right now. And we have 2/3. 1/3, 2/3. Maybe if I lay them down, you can see them better. There we go, 2/3. Well, we've got 2. Well, if I give this third one, give this third one. Okay, looks good. I distribute them evenly. This guy's happy. This guy's happy. They each got a whole. All right, all looking good. But in division, the answer is what one unit gets. What's the answer in division? The answer in division is what one unit gets. I don't have a whole unit. I have 1/3 and 1/3. That's 2/3. Well, so we have to look and say, oh, look at the guy that's over in Timbuktu. There's the other third. He doesn't have anything. Well, we need to be fair. If this 1/3 gets one whole and this 1/3 gets one whole, then this 1/3 also gets one whole. And the answer in division is what one unit gets. So if we look, 1/3 plus 1/3 plus 1/3 makes one whole unit. 1 plus 1 plus 1. 2/3. 2 divided by 2/3 equals 1, 2, 3. And students are blown away saying, but how could that be? We only started with 2 and we did division and we ended up with a larger value. We start with 2, we end up with 3. This doesn't make any sense. And then they start realizing they're dealing with a fraction. They're dividing by a fraction, something that is not a whole integer. And they will do 100 of these problems to convince themselves that this is actually what happens. When you take a whole number and divide it by a fraction, you get a larger value. Now, I know there's some tricks on how you can look at it when you say, well, I can just do this real quickly, but please don't tell students how to do it quickly, because we really want them to get the understanding of what it means. And they do, they figure it out. And then they say, oh, but I've done so many of these now, I'm seeing a pattern. And if I just multiply this by this, I get this and I'm all done. And they will figure it out. Between whole numbers divided by fractions, fractions divided by fractions, fractions divided by whole numbers. They do them all. And so that is another way that we use the materials to go from the concrete to the abstract. And they would say, okay, that's 2 times 6, that's 6 halves, that's 3. And they will get there. But we want them to understand how it actually works. Did that trigger any questions?
I just wanted to say that, Rita, it's Patrick, I'm sorry to jump in.
You're fine.
As you were talking about not sharing those secrets on how to, do the problems quickly, I think a big tenet of all of Montessori, throughout Montessori, is that we are process oriented more than product. So
Yes.
we want them to be able to do it and do it correctly and thoroughly before they start jumping those. So it's
Right.
always about the process in Montessori. Sorry to interrupt.
No, you are perfectly fine. A big thing that we do, and I went over word problems with some friends today, was I'm not that concerned about the answer. And they're like, oh, I got it, I got it. And I said, okay, what's your number sentence? How are you going to solve this? And they're like, well, I don't know, but the answer is $1.50. I'm like, okay, that's nice. You got $1.50. How did you get it? And they're like, oh, I don't know. It just, that's what makes sense to me. So then I back them up and say, let's figure out why that makes sense to you. And so it could be that you had the number of students, I'm just going to abbreviate, number of students times the time it took them to do something equals your total time. As we just put together a number sentence. And then I said, now you can plug in, well, it's 50 students now. It took them 2 minutes and you can calculate it. And they figure it out. If they can figure out the number sentence on how they did that one simple one in their head, they can go and apply it to so many different problems. And with some of the word problems that we have, some of our packets, they have figured out that, well, if I figured out for the first problem, then that's used on the second problem and third problem as well, and I'm golden. But it backs them up, like Patrick was saying, it backs them up to think about, what are they talking about? What does it mean? Because yes, some of the times, sometimes they can just do it in their heads and say, this is logically what makes sense. I don't understand why. And we're trying to get them to understand why, so they can apply it in more difficult situations to deepen their understanding. Okay. Any questions? Any other triggers? I mean, this is basically what we do. We do it in math, we do it in language, we do it in geography, we do it in chemistry, in physical sciences. Again, there's some experiments on our shelf over there. And on the first few, the main thing was, how are you writing it up? What are you doing? Do you know the different parts of the experiment? Do you know why you can only have one variable in your experiment to know whether it's going to be accurate or not? It goes through all of that. So we hit this in all the areas of study. And they're also integrated. Somebody said, in our reports, I know some experiments were listed under geography. Well, why are they listed under geography? I said, because they started with the basics physical sciences. And what's geography but gets into physical sciences. And so it's crossed, they're connected. Yes, you could just put it under science as well. But the areas of study are integrated. And the connections the students make are amazing. They're like, oh, this is happening because in ancient times this was going on, and then they were thinking about this and they were writing this, and then the merchant came, and on the Silk Road they were trading these different things, and then that got spread from this place to that place, and look at how things evolved. Fabrics is one of the big things. We did a lot on the Silk Road last spring, and I still hear comments about it this fall. Well, in the fall, now it's wintertime. I was still hearing comments about it, about how things were impacted and what was going on. So students are thinking about it. Months later, they're still thinking about it. I was surprised to hear the comments, but I heard them. And it's a wonderful thing. And they just make more connections every single day. So it's a wonderful thing to be able to work with these students and see what they're learning. They teach me every day, I think, and I'm just guiding them towards knowledge that we have and through the materials and then abstractly. And they're like, oh, I don't know if I can do that without this. And I said, do me a favor. After they've worked with the material enough, I said, all right, what are you doing? Show me on paper what you just did. Now use the material to check your work. As they migrate from the concrete to the abstract, sometimes they are very hesitant to do that migration and they need encouragement. And then they say, oh, I did it. Yeah, I just did it on the materials and it matched exactly what I did without them. And pretty soon those materials start fading away because they've got the full understanding. All these little steps just add right up. So I want to thank you for sharing your children with me, or sharing your future children with me, whatever the case may be. And it's a joy to work with them. And it's an amazing curriculum that we just get to expand on and carry things forward.